Okay, so let's start with number 2 in section 1.1, and the following differential equation is dy dx equals 2x plus 1, and we have an initial condition. Y of 0 is 3. And the directions say find a function y equals f of x satisfying the given differential equation and the prescribed initial condition. Okay, so here, right, this guy is our initial condition. Right, we obviously have our differential equation, right, and the goal, right, is to find a solution, and in this case a solution is a function of x, of one variable. So we know the general solution of this differential equation from the introduction video. So recall, right, y of x, which is what we're trying to find, or sometimes just called y. So in this case, right here we have, they just called it y, but it's the same y. Remember, this is just the integral of our function with respect to x, and then we're going to add a constant. And remember that this guy is your g of x. And one thing I forgot to write on the last, in the introduction, actually I want to write it now before I forget, is I want you to note that that g of x, okay, if I take the derivative of that, which I'm really taking the derivative of the integral, they're inverse functions, you should get your original function back. And our original function is f of x. Now the book likes to use this 3 horizontal lines to kind of represent an identity parallel here, but I'm fine if you just use the equal sign. Okay, so let's go ahead and integrate this derivative so we can find the solution. And let's see, problem was, what was the problem? 2x plus 1. Okay, so we had dy dx equals 2x plus 1. So I'm going to integrate both sides. So I'm going to, well, let me actually show it in the next step. Dy dx equals, and again I'm integrating this polynomial, right? But if I'm integrating that, I'm really integrating with respect to dx. Because again, if you remember, this is really just the area under the curve, and you can approximate this with rectangles that you learned in integral calculus with the areas of the rectangles, or Simpson's rule of trapezoids. But that's why the dx is there. So this guy, right, this is, you have a integral and you have a derivative, right? This guy is really y prime, and that's your integral. So derivative integral, I'm going to be left with y, or y of x. And when I integrate this polynomial, if you want, you can separate this as, and again, I'm going to write all the steps. If you want to skip some, if this is too much review, that's fine. Just want, again, I want to make sure everyone is on the same page. So I'm going to break up this integral as as 2x dx plus the integral of 1 dx. Okay, so I'm allowed to do that. And again, more specifically, I have a constant, so we can use the constant rule with integrals. We can take out the constant, and I'm just left with x dx. And I'm just going to leave this guy here. Okay, so 2 times, well, what is the integral of this guy? And here we're just going to use the power rule for integrals. So remember that when we integrate, right, x to the n dx, it's going to be x to the n plus 1 divided by n plus 1, right? The opposite of what we do with the derivative. So in this case, let me get my white. I'm going to have 2 times x, right? This is really the power 1, so I'm going to do x squared over 2. And I'm going to add, I'm going to integrate 1. Well, 1 is really, another way of looking at this is really the integral of x to the 0, because x to the 0 is equal to 1 dx. So if we add 1 to it, we get 1 over 1. And finally, all right, we're just multiplying fractions here, so that's gone, plus x. Now I integrated, so I need a constant. I have to add a constant. And let's see, maybe write my constant in purple. So y of x, right? This is my general solution to the differential equation. And one thing I want to point out, so since I split up my integrals, I mean technically here, after I integrated, which was, okay, this guy right here, I mean I could write a, if you want to say, let's see, this guy, x squared over 2 plus, I mean, technically, I should write, you know, some constant c1, and then after you integrate the second one, you can say, you know, add the second constant. Well, I mean, here I can just say this is c1 plus c2, but it becomes a little too cumbersome. We just need one constant. It's some arbitrary constant. So let's see, they want a solution satisfying the given differential equation and the prescribed. Okay, so we want to find a particular solution. Well, to find a particular solution, we have an initial condition, and our initial condition was, so we can have all this together, is right here. And our, let's write our y of x squared plus x plus c, right? So our solution is a quadratic function. And let's see, we have y of 0 equals, so let's input 0 squared plus 0 plus c, and y of 0 is 3. Well, all this is 0. So we have c is equal to 3. So a particular or unique solution, again, these are curves, a particular solution is the following. Y of x equals, and we have x squared plus x plus our c, and in this case our c is 3. All right, so there is our c. Okay, so now that we found our particular solution, I want to mention, well, let's look at the big picture here. So I pointed out this note part where g prime of x, right, was going to be equal to f of x. Well, remember, g prime of x is your integral, so I'm really integrating my integral. So I should obtain our solution, or f of x. So we integrated, so what happens if I okay, I'm running out of room, differentiate y of x, right, with respect to x. So, thus, that is, so that is this guy right here. If I find the derivative, y prime of x, I get 2x plus, and the derivative of x is 1, and the derivative of 3, a constant, is 0. And notice 2x plus 1 is what we started with, right? That's our dy dx. So it's a nice way of verifying that your answer is in fact correct. So again, there's your dy dx. So again, a nice quick check.